Welcome to class of physics. In previous videos we studied about the first part of this unit, that is vector analysis. Now we are going to start the second part of this unit, that is related to Maxwell's electromagnetic theory. So in this we are going to study about four different differential equations of Maxwell's electromagnetic theory. Maxwell's equations are basic equations of electromagnetism, which includes Gauss law for electricity and magnetism, Faraday's law, and Ampere's circuit law. Maxwell's four differential equations are del dot E, so that we call it as divergence of electric field E is equal to rho by epsilon naught. The second equation, del dot P, that is divergence of magnetic field, is 0. Then third relation is curl of electric field is minus dou B by dou T. And the last relation is del cross B equal to mu naught J plus mu naught into epsilon naught dou E by dou T. These four are the differential equations of Maxwell's electromagnetic theory. And these are valid for all kind of electromagnetic waves like light wave or it may be radio waves. So here we have to derive these four differential equations by using four laws. So one is Gauss law for electricity, and the relation is Gauss law for magnetism, and Faraday's law, Ampere's law. Each law will produce different differential equations. The first relation is obtained by using Gauss law for electricity. And the second relation is derived by the same law, Gauss law for magnetism. And the third relation is derived by using Faraday's law. The fourth relation is derived by using Ampere's law. For that, first we should know about these four laws and their mathematical expressions. Then only we can deal with these electromagnetic waves relations. And the one more basic concept used to derive these equations are theorems, Gauss divergence theorem and Stokes theorems. Here, using Gauss divergence theorem, we can convert the surface integral to volume integral and vice versa, volume integral to surface integral. Similarly, using Stokes theorem, we can convert surface integral to line integral and line integral to surface integral. Gauss divergence theorem includes the divergence relations. Stokes theorem includes curl relations. Here the first two relations are divergence of electric field and divergence of magnetic field. So here we are using Gauss divergence theorem. And in third and fourth relations, there is a relation of curl between a vector. So curl of electric field and curl of magnetic field. To derive these relations, we are going to use the Stokes theorem. So these derivations are very important. So they may ask for 2 marks, 5 marks or 10 marks. They may ask relations for 2 marks or derivations for 5 marks. Along with that, there may be a problem. Now let's derive relations one by one. So today I am going to try to derive first two relations, divergence of electric field and divergence of magnetic field. Okay, Maxwell's first equations. Maxwell's first equation is based on the Gauss law of electrostatics. The statement is mentioned here, which states that the flux passing through any closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. Okay. Here the surface is closed surface and the flux passing through that closed surface is equal to charge enclosed divided by epsilon naught. So 1 by epsilon naught times the charge enclosed. So Maxwell used these relations as a beginning to derive his first relations, that is divergence of electric field is q by epsilon naught. So what is that relation? Divergence of electric field is equal to q by epsilon naught. So now we have to reach to this relation by using this Gauss relation. The Gauss relation is in terms of surface integral, but we have to convert this into the divergence of electric field. So for that, several different steps we are using. So actually this is not q, it is rho by epsilon naught. So charge density here we are using what you written in first place. Yes, it is rho, charge density. In Gauss relations, this q indicates the charge enclosed by Gaussian surface. Suppose a rho indicates a volume density of charge enclosed by the surface S. Okay. Here the relation between density and the charge. So what is density? Density is rho equal to charge per unit volume. Charge per unit volume. So that is the volume. So actually this is the density. Now what about using this relation? We can write q equal to rho into phi. So phi is the volume, rho is the charge density. But here we don't know how much volume enclosed. For that we are going to take a small volume element as d tau. So that the total charge enclosed is integral of the charge density into the volume element d tau. So this is the volume integral. For that we can write the charge in terms of charge density, q equal to integral of rho to d tau phi. Substitute this q value in the above relations, the Gauss expressions, that is circular integral of eva dot ds equal to, here the q, replace this q by this relations, then it is 1 by epsilon naught integral of rho into d tau. So here the Maxwell equation is in terms of divergence, but here it is a surface integral. Now we have to convert this in terms of divergence. For that, using Gaussian divergence theorem, we can convert the surface integral into volume integral. Along with that, we are going to write the divergence term. So that when you convert this into volume integral, then we can write del dot E into d tau. Here this ds is the surface integral, that small surface element. So now for volume integral it becomes d tau. For that, the right hand side remains as it is. So what is the right hand side? 1 by epsilon naught integral of rho d tau. See here left hand side and right hand side, both these are integral, so that is volume integrals. So this is also volume integral, this is also volume integral. Uniformity is there. Now bring this left hand side term to, so right hand side term into left hand side, then it becomes minus. For that, integral del dot E d tau minus of 1 by epsilon naught rho d tau is equal to 0. Because of these two are the same integrals, volume integral, for that write a common term. So volume integral of del dot E minus rho by epsilon naught d tau is 0. Here this volume integral is equal to 0. That indicates the integrand is equal to 0. For that, since the integral is 0 for volume enclosed by arbitrary closed surfaces, the integrand must be 0. For that, del dot E minus rho by epsilon naught is equivalent to 0. Then finally we can write del dot E equal to rho by epsilon naught, which is the required relation. That is Maxwell's first relation, del dot E equal to rho by epsilon naught. Here in other words, we can write this as del dot D equal to rho. What is this del dot D? So this is also the same relation to equivalent to this Maxwell's equations. For that, the D is equal to as density, D equal to epsilon naught into E. So when you take this epsilon naught into left hand side, then it becomes epsilon naught into E. That epsilon naught E is replaced by del dot D equal to rho. So you can use any relations. Del dot E is rho by epsilon naught, or del dot D equal to rho, that is divergence of electric field is equal to rho by epsilon naught. This is the first relations of Maxwell's, which is derived using Gauss law in electrostatics. Similarly, the second equation is derived again using Gauss law in magnetostatics. Okay. So Maxwell's second equation is based on Gauss law in magnetostatics, which states the flux of magnetic field across the closed surface is always zero. In mathematical expressions, we can write B dot ds equal to 0. What is B dot ds? This is the flux, magnetic flux through a surface area. This B dot ds indicates flux. This flux is equal to 0 for a closed surface. If it is open surface, then this relation is not valid. Okay. This is for closed Gaussian surface. So this relations here, n is outward drawn. Here we are not using unit vector n cap, we are writing directly a vector ds. So using Gauss divergence theorem, we can convert this surface integral to volume integrals. Here, what is the second relation of Maxwell's relation? The second relation is in del dot b is equal to 0. So divergence of magnetic field is 0. So we have to convert this integral form to divergence of vector field B. So using Gauss divergence theorem, we can convert this surface integral to a volume integral, along with that the del operators. So integral of B dot ds, this is surface integral. Now we are going to convert this into volume integral, then it will take the divergence term. So this becomes del dot b into d tau. Okay. So take this relation again, so which is equal to 0. The volume integral del dot b d tau equal to 0. If the integration is equal to 0, this integration is equal to 0, that indicates the integrand must be equal to 0. This integrand must be equal to 0 for that del dot b equal to 0. So which is the second relations of Maxwell's equation. So like that to derive these two relations. Okay. So this is enough. In next class we are going to derive two more relations using Faraday's electromagnetic induction law and Ampere's circuitry. Thank you.